Now that we know what a free body diagram is, we're going to take a look at free body diagrams that deal with angled forces. So if we take a look at our example, we can see that we have a car that is parked on a hill. We can also notice that this hill is on an angle. So if I were to draw the ground real quick, I would see that this ground and the hill are making some angle here. This is going to be very important when we construct our free body diagram. And just a reminder, a free body diagram is just a way of showing the forces that are acting on this object in a given situation. So our first step is going to be draw a dot for the car. So here's our dot that represents the car. And then we want to set up a coordinate system that is parallel with the surface. So in this problem, the surface is right here. So as you can see, my coordinate system is parallel with that surface, and parallel just means that they're both going in the same direction. So the first thing we want to do when approaching a problem like this is list all the forces acting on our object. In this case, that object is our car. So we want to think about what forces are acting on this car while it is at rest on the hill. Well, let's start off with the easy force. We always know that gravity is acting on an object. We also know that gravity always points down. The next force that should be easy to identify is normal. And we know that normal points up from a surface. In this case, though, the surface is not a flat surface. So we need to remember what we talked about, how normal points perpendicular to a surface. So we need to remember that when we're saying up from a surface, that's just referring to perpendicular from that surface. And perpendicular, again, just means a 90-degree angle. So if this is our surface, perpendicular would be pointing this way, up from that surface, but not straight up, forming a 90-degree angle. The last force to think about is the force that's keeping these tires from moving right here. And we know that a force that opposes motion is friction. Now that we've listed all of our forces, let's go ahead and draw what these forces look like on this car. So since the ground is at an angle, the normal arrow should be up and perpendicular from the ground, just like we said over here. So it should look something like this. Next, we need to talk about gravity, and we know that gravity is always going to point straight down, no matter what is going on in our problem. And it points straight down because it's pointing down towards the center of the earth. Our free body diagram should look something like this to the right. We see right here that we have this dot representing our car. Then we have a downward pointing arrow representing gravity on the car. Then we notice that we have force normal pointing up at an angle. It's at an angle because it's perpendicular with the surface. And then we see that we have friction pointing parallel to the surface and to the right. So why would friction be pointing to the right? We need to think, what direction would the car start moving in if we were to remove the brakes? It's pretty obvious to see that if the car is on a hill, the car is going to end up moving this way. So since the car would move this way, we would have to have friction in the opposite direction, which is where we have our friction on our free body diagram. Next, let's talk about the balance forces acting on this car. So thinking about this problem again, we said that the car is at rest. And we also said that our free body diagram looks something like this. We have force gravity pointed down, force normal pointed perpendicular to the surface, and then we also have force friction pointed to the right. When an object's motion is at rest, it means that the forces acting on that object are balanced. So we know that our car is at rest here. So what forces are balanced? Well, this is a little tricky because we have all these forces acting in all different directions. If we were to go ahead and draw a horizontal line on our diagram, we can see that force normal and force friction are both pointed up above that line. They may be pointed at angles, but they're both pointing up. We can also see that force gravity is pointed down. So what does that mean? That means that the normal force and the friction force together will have to equal out gravity. How do we know that? Well, we said that our car is at rest. So if our car is at rest, the forces must be balanced. What forces are unbalanced? There's none. Again, since our car is at rest, it is not moving. None of the forces are unbalanced. Everything on this diagram needs to be balanced for our object to be at rest. So a more detailed answer of that is seen in the diagram to the right. Right here, like I said, we have the normal force on the car, the force friction. If we were to add these two together, they would equal the force of gravity. And we could see that if we were to just kind of like break them down into their x and y components. So remember, a graph, right, looks like this, where this is like negative y values, these are positive y values, these are positive x, and these are negative x values. If we were to take force normal and split that up, we would do the same. So we'd go straight down and then to the right. So we see that this is our x, this is our y, and then same thing for force friction. We go up and then to the right, this is our x, this is our y, just like that. We could see now that we only technically have two forces acting in the x direction. So part of force normal and part of force friction are both acting in the x direction. But we can also see that these two forces are equal in size and opposite in direction. Therefore, they're going to cancel each other out. Now, if we look at the y direction, we see force gravity, we see how long it is, but then we also see that we have force normal pointing up and force friction pointing up. These two, like we said, added together are going to equal gravity and cancel that out. So everything in this problem is balanced. Next, let's take a look at a mountain climber who stopped on the side of a mountain. Our first step is to draw a dot for the climber and then set up a coordinate system, again, that is parallel with the surface. So here's an example of what my coordinate system should look like. I have my climber represented by this dot right here, and then my coordinate system that is parallel with the surface. So this line right here should represent my surface or the mountain. First step is the same as before. We want to list and draw all the forces acting on the climber. Well, we need to remember this climber is on Earth. So when drawing and listing all the forces, let's always start with gravity. We know gravity is always present in every single problem. And again, we know that gravity is always going to point down. We can see in this problem, though, that the mountain climber is on the mountain. So the mountain right here is a surface. Because it's a surface, it's going to exert a normal force. Again, when we say that a normal force is pointing up from a surface, we mean that it's pointing perpendicular. So the normal force should point in this direction. The last force that we can identify is force tension. The problem told us that the mountain climber is holding onto a rope. We know that a rope will exert a force tension. So here's an example of what our free body diagram should look like. We have force gravity pointing straight down. We have force normal pointing to the left. And it's pointing to the left in this case, like we said before, because that's perpendicular to our mountainside. Then we have force tension pointing in the same direction that our rope is pointing. And that is always going to be the case. Force tension is always just going to be in the same direction that our rope or string is pointing. We can see that in this problem, only one force is at an angle, and that's force tension. So if we go ahead and split up force tension like we did before and think about our x and y axes, we have positive y here, negative y here, positive x over here, and negative x over here. And if we were to split this up, we have force tension in the x direction, force tension in the y direction, gravity pointing down, and force normal pointing to the left. Again, we're dividing force tension up because it's at some angle here. Since force tension in the x direction and force normal are the same size but pointing in opposite directions, they're going to balance each other out. In addition, we have force tension in the y direction and force gravity. We can see that force tension in the y and force gravity are the same size and pointed in opposite directions. Therefore, they're also going to balance each other out. In conclusion, there's no unbalanced forces because we are at rest. Summarizing what we just talked about with angled forces, the most important step is going to be listing and drawing all the forces that are acting on your object. You need to remember though, and this is the part that a lot of people mess up on, is that force normal will point perpendicular. And again, what we mean by perpendicular is that force normal is not always pointing straight up. Another really important thing to remember is that force friction is going to point parallel to our surfaces. So what we mean by parallel is that it's just pointed in the same direction as our surface. So if this is my surface, friction is pointed in that exact same direction at that exact same angle. But if we were to have a surface that is at a different angle, like let's say a surface right here, that is a triangle, and my box were to be on this surface, friction would most likely point in this direction if the box started to move. Again, it is in the same direction as the surface, and that can either be left or right, but we need to make sure that we're reading the problem so that we know which direction our object is moving in. If it doesn't tell us the direction that the object is moving in, then we need to use common sense to realize that if an object is on an incline, friction is going to be pointing up that incline. Because if that object were released, it would move down that incline. And we always said friction moves in the opposite direction of motion.